Welcome to Pomodoro Joe for Tuesday, July 4th, 2023. As you can see, this is my second time recording this. All right, today we're doing LeetCode problem 137, single number 2. This is a medium problem. Given an integer array nums, where every element appears 3 times, except for one, which appears exactly once, find the single element and return it. Okay. You must implement a solution with a linear runtime complexity and use only constant extra space. So this suddenly went from a medium to a hard problem. All right. So as I mentioned, this is my second time recording this, so I apologize if I'm a little bit less enthusiastic this time. All right. So given this first statement, you have an array of nums where every element appears 3 times, but one appears exactly once. You want to find that one element that only appears the one time. So a simple way to go about doing this is just to go through, count all the elements, or how many times an element appears. You could have a dictionary where the key is the element and the value is the count. So you go through, count them, or you can use Python's built-in counter to count them. You could also use a set. Anyway, given this basic statement, it's not that bad. However, given this condition where you have to use a runtime complexity that's linear and only constant extra space, that suddenly makes this problem a lot harder. So for one thing, this constant extra space, let's talk about this one first. Constant extra space means you can have some extra variables here, like an integer, but you cannot use any variables or any data structures that grow with the input. So for example, a dictionary where you have values that are the counts and keys that are the numbers, well, that's going to depend on how many numbers we have in the input. So if we have 100 numbers in our input, 99 of them will be triplicates, so 33 of these numbers will be our keys, and the values will range from 1 to 3. So if we use the dictionary, it will grow based on how many numbers are in the input here. The fact that it's growing, like the dictionary will grow and the set will grow, anything that grows, an array where you append elements to the array, those things are not constant space. Those data structures grow in size as the numbers grow in size. So if we had this input, it has 4 elements, we might have 2 entries in our dictionary. But if we had this input, which is 3 unique elements, we might have 3 entries in our dictionary. So that means this is not constant extra space. So constant extra space means we can use things like integers. So constant extra space means we cannot use data structures that grow. So things like sets, dictionaries, arrays that are growing over time, those are all out. We can't use them. All right, now let's talk about runtime complexity. So this is saying we have to do a linear runtime complexity. So one option, we might say, okay, we can't use data structures that grow over time. So one thing we could just do is go through, check every number and see if it's in the array again. So we just look at the first number, then we check for that number in the array. Then we look at the second number, check for that number in the array again. Check the third number. So we basically, for every number, we go through the entire array again looking for that number. If we don't find it, then that's our unique element and we can return it. However, the fact that we're going through every number in our array and we have to compare it to every other number in the array, that means we have to do an n times n runtime. That means every number in the array is compared to every other number in the array. That is an exponential runtime. That is not a linear runtime. Linear runtime means that we go through our nums once, or a set number of times, once or twice, but you can only go through this set of numbers a set number of times. You cannot go through them for every number in the array. So how do we solve this problem? So the approach to this, we know we can't use these extra space type data structures. So if we're not allowed to use these extra space data structures, we probably have to do some math. We have to look at how do we add these numbers, subtract these numbers, divide these numbers. What math can we use? All right, let's put 25 minutes on the Pomodoro timer and we'll get started. So what do we know about these numbers? We know that every element appears 3 times, except for one of them. So we know that if we add all these elements together, if we sum these elements, we know that value will be divisible by 3 if we remove the one element that only appears once. So we could add all these numbers together. divide it by 3. Well, if we divide by 3, we probably won't get something divisible by 3. So if we sum all these numbers together, then we go through, individually remove one of the numbers from our sum. If we divide that by 3, if it's evenly divisible by 3, then the number that we removed possibly might be the number we're looking for. Now I say possibly because, as you can see with this example, it won't always work. So if we have 0, 1, 0, 1, 0, 1, 99. Okay, so this adds up to 102. 102 is divisible by 3 because 99 is divisible by 3, and 1 plus 1 plus 1, 3, is also divisible by 3. So if we had 102 divided by 3, let's check 0. We remove 0 from the sum. Well, that's just going to be 102. That's also divisible by 3. So 0 might be the number that we're looking for. It's not, we can clearly see that, but from the algorithm standpoint, we might think that's the number we're looking for. So we'd have to do some extra check to see, is this really the number that we're looking for? So that extra check, we would probably just go through our array one time, looking for 0 again. If we find 0 again, then it's not the number we're looking for. Then we go to 1. We subtract 1 from 102. Now 101 is not divisible by 3, so we know that 1 is not the number that we're looking for. Then we move on to 0. Oh, once again, this one could be the number, so we have to check, is this the number? Oh no, it's not. And then finally we get to 99. Now 1 plus 1 plus 1 is divisible by 3, so 99 could be our number, so we have to check the entire array for 99 a second time, and then when we don't find it, we can return 99. So that's our approach here. We'll go through, we'll sum all of the elements in the array. Then for each number in our array, we'll subtract that number from the total. We'll divide by 3, actually we'll do a modulo by 3 to see if the result is 0. There's no remainder. If that sum is divisible by 3 evenly, then the number that we removed could possibly be the number that we're looking for. Then we have to do a linear search through our array, looking for that number a second time. If it doesn't appear, that's our number, we return it. If it appears a second time, that is not our number, and we have to keep looking. So this is the sort of medium approach to this problem. Now, I will point out it doesn't completely satisfy our constraints here, but it's pretty close. So let's try it. So we'll have some total to start with. That'll just be the sum of our nums. So we could go through basically just every number in our nums and add it to some total. That's a linear operation. We just have to go through the numbers one time and sum their values. So this is linear and this is constant extra space. We just have one total here. It doesn't grow based on the amount of space it takes, doesn't grow based on how many numbers we have in our nums. Okay, then for every number in our nums, we will get some subtotal, I'll call it. That's just the total minus this number. Now, if this subtotal is evenly divisible by 3, then the number that we removed, this n, is quite possibly the number that we're looking for. So if our subtotal modulo 3 is equal to 0, then we have to check, is this the number that we're looking for? So we'll create a helper function for this. If is the answer, and we'll pass in n. If this is the answer, then we'll return n. Otherwise, we have to keep going. Now at the very end, we don't really know what to return, so we can just return whatever. At this point, we should never reach this, so I can say return 0. We'll just leave it out, actually. Let's make sure that we actually return n here. Okay, so we don't have this is the answer. Let's create a function to help us out. If is the answer, and we'll take this option. Now we have to go through our entire array again and keep a count. So we have a count starting at 0 for n nums. If n is equal to this option, then our count is increased by 1. At the end, we just return count is equal to 1. If we only found one of these, this is our answer. If we found more than one, then this is not our answer. Okay, so this solution is okay. Like, it's linear in terms of we only go through our nums one time, subtracting them here. And this is linear as well. We only go through the nums one time to see if we have this number more than once. But it's not quite right. If you look at this, this is the answer. is embedded inside of this for loop. So we essentially have this for every number in nums embedded inside of every number in nums for loop. That is an exponential runtime. Now in practice, this probably won't be exponential because most likely we'll only have a small subset of numbers that we'll call this function. However, in the example here, 0, 1, 0, 1, 0, 1, if these ones say were 3s, then every single number that we can have from this sum is divisible by 3. So we would end up calling this is the answer for every single number in our list. That makes this an exponential runtime. So this is close to our answer, but it's not quite right. All right, let's just see if this works. Okay, so this works. Now, this doesn't really fit our criteria. It's pretty close, but it's not quite there. All right, and it only beats 19% for runtime and 66 or 86% for memory. All right, so we can jump in and take a look at some other solutions. Let's see what other people are doing. Let's just grab one here. So this one uses a set. So that one also doesn't really conform to the constraints. A set will grow over time. This is not constant space. Let's see what else we got here. Looks like we have some arrays and they're appending to the array. Again, not constant space. Those grow with the number of inputs you have, so that's not quite right either. Dictionaries, yeah, so a lot of these solutions are not really conforming to the constraints. Okay, so in order to conform to the constraints, we have to do some more complex math. All right, so let's toss this out and start over. Unfortunately for the solution I'm about to show you, I don't have a good way to derive the solution, but maybe I can describe it. So for this one, it'll be a bitwise operation. We'll keep track of the number of times we've flipped the bits. So for this, we have a ones count and a twos count, or yeah, I'll call it ones and twos. I'll call it flip count 1. Starts at 0. We haven't flipped any bits yet. And flip count 2s. Okay, so for every number in our nums, all right, so the first time we XOR, it's going to be n XOR with 0. That just gives you n back. Then if you had n in flip count and you XOR with n again, so we find the same number a second time, n XORed with n gives you 0 back. So essentially every other time you see n, it flips from having n in our flip count or having 0 in our flip count. So if n is repeated 3 times, the first time we see n, it'll be represented in our flip count 1s. Second time we see n, it will be removed from our flip count 1s. The third time we see n, it will be included in our flip count 1s. Now what we really want is on that third time, we want it to be removed from our flip count 1s. So in order to do that, we need to do this second piece. So we have and this with the inverse of our flip count 2s. Okay, and we'll get back to that in a minute. So our flip count 2s, this is very similar. It's going to be flip count 2s XORed with our n. But this one we will AND with our flip count 1s inverse. Okay, so again, I don't have a great way to derive this one, but I can describe it. So flip count 1s starts at 0. When we XOR it with our n, it becomes n. We'll AND it with the inverse of our flip count 2s. Now flip count 2s starts at 0, so the inverse of flip count 2s, 0, 0, 0, 0, becomes 1, 1, 1, 1, 1. So that's a complete mask that's all 1s. So this will just retain our n. Now when we get to flip count 2, when we do this first XOR, it starts at 0, XORed with n, it becomes n as well. But now we'll AND it with the inverse of our flip count 1s, which at this point contains n. So when we take n and we invert it, it means that all the ones that were 1s in n become 0, and everything else becomes 1s. So that basically makes this, which is n, and this, which is not n, become 0. So n and with not n is 0. So our flip count 2's becomes 0. So first pass, or first number, flip count 1's becomes n, flip count 2's stays at 0. Next time you run across that same n, now our flip count n with n, that will be 0. So n XORed with n is 0. Now when we AND it with our flip count 2's, it doesn't really matter what this is because this was 0. So we keep 0 at our flip count 1's. So flip count 1's is now back to 0. Now flip count 2's. Well, our flip count 2's was 0. Now we'll XOR that with n. So this becomes n. When we AND it with the inverse of 0, so that's just 1, this stays n. So this whole thing went from 0, 0 to n, 0 to 0, n. So once again, they both start at 0. This one becomes n, this one becomes 0. This one becomes 0, this one becomes n. Next time around, this one is 0, XORed with n becomes n. This one is n, but when we do the inverse of n, that's n and not n, so flip count 1's becomes 0 again. So essentially, when we go through all of our numbers, if we have 3 of them, it goes from that number back to 0 to that number and then back to 0 again. So that means for every triplet that we have, it starts as 0, then it becomes that number, and then it goes back to 0 on the third pass. This is perfect. That means that all of our numbers will 0 each other out, except for the one that appears exactly once. So at this point, we can return our flip count 1's. Okay, let's try this. We're almost out of time, so let's try it. And it works. So this is the, quote, proper solution. But in my opinion, this is not a medium problem if that's the proper solution. This is a hard problem. All right, so we are out of time. That is it for me. I hope this made sense. If not, I'm going to try to do a write-up, and maybe I'll leave a link in the description. All right, hope you had fun. Hope you learned something. Hope you enjoyed this. Hope you can go out and write better code.